So in the context of supervised machine learning algorithm, one of the most powerful technique that has been established in the recent years is what we call as ensemble learning. Now, this technique uses a process called, um, mm, so you have many different machine learning algorithms which work in pipeline. They work in tandem towards making a single prediction. So all models put together towards making a single prediction. That is the idea behind ensemble learning technique. And one of my favorite ensemble technique is what I call as the random forest model. I love it. I mean, if you ask me which particular model do I use many models, but random forest is something, it makes me crazy. If you really have understood the subject, you will feel love for it. Okay. So the idea of random forest is it works on a technique called bootstrap aggregation. Just let me understand how many of you have heard this word random forest. So the technique uses something called as a bagging or bootstrap aggregation. So what is this? We generate or create many different training subsets, or what we call as a bootstrap sample from the initial training data set using uh, with replacement. All it means that the bootstrap samples that you have created is created by selecting randomly some observation from your training data set, and there could be some observation that are repeated. They may have repetitions. So every different bootstrap sample that you have created are uniquely different or distinctly different from each other. Okay, but there may be, as I told you again, there may be some repetition of the observation. So why we do it? We try to plant random trees in a forest. That is why the name, and this tree refers to decision tree. Okay, so as you randomize the trees in its attributes, that makes the forest random, and that is why the name random forest has come. Okay, so that makes every different bootstrap sample distinctly different from each other. So what we do then is build a decision tree model corresponding to every bootstrap sample that you have. So therefore, every decision tree is going to be uniquely different from each other. Now, when you pass or test any out of the sample, out of the data set sample, using all the decision trees, every decision tree is going to give a different classification. Am I right? So what we are going to do at the end is look at that particular observation, what vote it has received. That means that particular observation must receive a vote, maximum vote or a majority vote for a particular class. If that tested sample has been voted for one, majority of the class predictions are one, then that particular observation will be labeled as one. So an unseen data will be exposed to a decision tree one. The same data will be exposed to another decision tree two. This way, multiple decision trees. Okay, in multiple different situations, multiple different contexts, that same unseen data will be exposed to. So it is usually seen that given the situation and conditions, that prediction of all these decision trees will kind of merge towards an identical classification, whatever may be the situation. To give you, because this may be an interesting thing, but a little difficult to understand. Suppose I claim I am a good student. Okay, I've been tested in Maharashtra, I've been tested in Karnataka, I've been tested in Delhi, I've been tested in, say, some other place, and everywhere I have been certified as a good student. That means with a under the given situation and the background, I have always qualified to be a good student. That means majority of the states where I have studied or where I have completed my education has certified me as good. Therefore, suppose my own state, which is West Bengal, have certified me as bad. Okay, that doesn't mean I'm really bad, because majority of the students and majority of the states have identified me as a good student. Okay, so I can be called a good student. Does it make sense? Okay, okay. So exactly the same philosophy is applied here. So the unseen data will be exposed to a variety of decision tree, and based on a majority voting scheme, the class that is identified will be labeled to that particular unseen data. That is how the random forest model works. Okay, so it is in random forest. What we typically do is, this is the interesting thing. We kind of randomly choose samples from an initial training data set, of which you would see some observation I said might have repetition. But it is always seen that when creating a random forest model, every bootstrap sample that you have created will leave 37% samples in your training data untouched, left out, or that has not been taken into consideration when doing this bootstrapping. This 30, why this 37% can also be explained statistically. We'll be running short of time, but you can always ask me. It is a very nice, interesting proof, provided you have understood the concept of probability. Okay, so it is not the, because I see many people say it's the same set of 37% sample. No, for this bootstrap sample, there will be one set of 37% sample in the initial training data set that will be left out. For this particular bootstrap sample, there will be another set of 37% from the initial test data set that will be left out or that will not be considered. This way, to every bootstrap sample, there will be a corresponding 37 missed out data that have not been considered when bootstrapping. Okay, so this 37% sample is what we call as the out of bag samples. Now, this data set is used for validating the model. But now you may say, well, as you have understood, in any supervised machine learning algorithm, we split the data into test data and training data. And test data is the one that is used for model validation, testing model performance. But then why do we need another additional out of bag error? So the reason being, hear me out carefully, out of bag error does give you an estimation of the model accuracy, but more importantly, it tests the variation in the training data. So if you are, if there is a lot of variability in the training data, the out of bag samples will give an error when applied to the bootstrap sample. So what I'm doing is I'm repeating this thing again. So you are creating a decision tree model corresponding to each bootstrap sample. Okay. Now I have that out of the sample data or out of bag sample, which I'm testing on each of the decision tree, and it is giving me some error. So all these errors, which are corresponding to those out of the bag samples for all the bootstrap sample, is averaged out, and that is what we call as a final out of bag error. So that out of bag error gives me a clue, an indication about the variation in my data set. So just think about it. If the data has a strong variation from, you have no head and tail of the data, there's no pattern, then obviously the model that will be trained will not be so strong model, or it will be not so a confident model that it can predict correctly any unseen data. There is some bit of, inconsistency in prediction. So obviously, that will reflect in the accuracy of the model. So if you have your out of bag error large, that will eventually lead to a lower accuracy of the model. Is that clear? So that is the main idea behind using the out of bag error also as an index for the model performance when it comes to random forest model. Is that clear? So we are soon going to close down the session now. So we have seen that if we have planted like beyond 200 trees, this out of bag error remains almost constant. There is no significant improvement in the out of the bag error. And also we wanted to randomize the forest using a factor which is called as the mtry factor that actually eventually randomizes the forest. So more you make the forest random, the better the model is. That's the sole idea. So we have seen that mtry value. So I'm again not going, what is this mtry? Possibly that will be kept as a separate note. But an mtry of 4 yielded the least out of bag error. So what we have done, therefore, using a maximum plantation of trees, which is equal to 200, and mtry value, which is equal to 4, we have calculated the out of bag error, which comes out to be 7.87%, not bad. And my accuracy is very high, close to 98%. That means this is a super model, the random forest model. So here comes the conclusion of the studies. Out of all these models, where I have seen logistic regression gave me an accuracy of 87% with no overfitting when tested using lasso regularization. And then when testing with decision tree, the model accuracy came down, which is 76%. And using a random forest model, it gave me an accuracy 98%. So I need a quick answer from all of you. Which model, therefore, I'm going to use? Good. Any other answers? I want everyone to be participative. Don't worry, I'm not going to end soon. Okay? Fast, more answers. Good, good, good. That's it. So, yes, it's a random forest because that's how we see anything having the highest model accuracy. But idealistically, that's not how it works. To give you an example, whenever you talk about a technology, be it in the manufacturing sector, be it in the service sector, IT, and so on. You have two parts to the technology. One is what we call as the development part, and the other is what we call as the implementation part. So at the development stage in manufacturing, it could be a prototype model development, a physical model development. And remember, prototype does not always mean physical models. It can be a new idea also, which we call as prototype, or it could be some concept, new concept. So we test or validate that concept, idea, or the physical model, okay, and then see if it can be really implemented or not. Same way in AIML, the first thing is, you remember, data is the heart of AIML. Without data, AIML makes no sense. Okay. Now, in India, many manufacturing companies are kind of adopting to AIML, and the biggest challenge to them is data acquisition. This is the biggest challenge. More investment is done, more time is taken just to capture data from different sources. Okay, it could be manually entered data, it could be machine generated data, but data is a challenge. Now, suppose in my company, for example, we have a data science team, those who have worked on a problem and they have come up with some model which looks to be apparently the super model, like a random forest, which gave me an accuracy of 98%. Now, for the data science team, it is not a big challenge because they are all working within the deadline. Their job was to finish it before the deadline. And they took, say, maybe a few hours or few days to build up that random forest model using the available data. Okay, but now that same model is going to be implemented at the implementation end. Now just think, if the same random forest model, though it may have an accuracy of 98%, but it is taking longer processing time to predict an unseen data, say maybe a few hours, or while you need that prediction to be made in few seconds or minutes, but instead it is taking longer hours or longer duration. Don't you think that the operator or the end user would be irritated? Okay, so he will possibly, because industries think from the point of result. If there's no output, that's useless. Okay, it may be some eureka for you, but not for them. So in that case, if they find a decision tree model or possibly a k nearest neighbor model or a logistic regression model, which might have accuracy lesser than the random forest model, but it gives a much faster processing time, they will definitely go for that. So you have to make sometimes a judicious choice. So as a part of the data science team, you hand over the model, but that model may be unsuccessful in making the right prediction. Okay, so that's where the challenge comes. So your model is good, but it is of no use to the implementation team. So if the entire model has to be scrapped, you have to again work from the scratch. So these all challenges are there. So that's all I had to tell you. So now I give you access to unmute yourself because I'll stop sharing.